This approach to working problems actually is used later on in chemistry too.
So we're doing part 7.
Part 6. What was part 6?
Oh, okay.
No, what was part 6?
It's Hess's law.
Yeah.
Okay.
Oh, no. We're going to hold part 7. Good call, guys. Yeah, actually, we couldn't do 7 until we did 6. So 7 would be very confusing without 6. So all that I said was right. I just didn't have the right slides up. Okay. So let's see if you like it. Anybody in here like to play puzzle? Like you have a 500-piece puzzle, 1,000-piece puzzle?
I love puzzles.
Oh, like puzzles? This working this sort of problem reminds me of working puzzles. We'll see if you guys think so or not. All right. So all Hess's law says is that if you have a chemical reaction, and to me, I kind of visualize it this way. If I have an overall reaction, and this is my overall RxN, okay, blah, blah, reactants goes to form products, okay? If I have an overall reaction, and if I can describe that reaction in, let's just say 5 steps, you know, where I have reactants go to form products, reactants go to form products, and I'm going to have to kind of show you how do I add up a chemical how do I add up these 1 through 5? How do I add reactions? And it's like you might imagine, I'll show you here in a minute. Basically, you add all these together, and you add all these together. These come down to here, and these come down to here. Okay, so that's how you add up chemical reactions. But Hess's law says if your overall reaction of interest can be described in a series, and I've written 5 up here, series of other reactions, okay, then the way this works is, we've talked about enthalpies of reaction, so that's delta H of Rxn. So I'll have a delta H of Rxn for each of these 5. 1, 2, 3, 4, 5. Okay, then guess what? All I got to do is add these together, and that's my delta H of my reaction of interest. That's kind of how that works. And I'll kind of show you what that means. So the simpler reactions that it's referring to is 1 through 5. It could be 2, it could be 4, it could be 20. Oh my gosh. But these people who like playing with puzzles, these are your puzzle pieces, okay? And this is what you need your puzzle to look like, right? So, there you go. And this is an OpenStax figure, and I was like, this is my second semester to teach Gen Chem from this textbook, which, you know, it's an open textbook. I was like, what in the heck is this saying? So let me digest this to you. This is actually, I would call it more of an energy diagram. H, of course, is enthalpy. So I could put energy over here too. Enthalpy, energy, right? And so as you go up, you have higher energy. If you go low, you have lower energy. I'll show you how this translates to a Hess's law problem, or to Hess's law. If you look at the first step, we could call it this. We could say that I have solid carbon reacting with 1 mole of O2 gas to form CO2 gas and 1/2 O2. So looking at this is where that looks like. Do you see this guy right here? That's my reactants, and that's my product. Okay, and that's my 1. Go back. 2 looks like this. 2 looks like this. It takes, well, let's put it up here. Then I basically take these products. So I'm going to take 1 mole of CO2. I'm sorry, CO. 1 mole of CO plus 1, and it's in its gaseous state. Whoop. Plus 1/2 mole of O2, also in its gaseous state. And voila, it's going to form 1 mole of CO2, also in the gaseous state. Right? What do I do? Do we know the enthalpy changes? So how do I want to do this? That one is number 2. Puzzle piece number 2. that one up here. Delta H of this reaction is negative 111, and that's kilojoules because it's associated with that balanced equation. This one, delta H of that second reaction, it is negative 282.5, also kilojoules. Exothermic, I think so. Negative, energy is released. And like the caption here says, it makes sense that energy is released because my reactants are way up here with energy, and my products in both of those steps have less energy. Where'd the energy go? That was released. It's an exothermic reaction. Okay, so that all works. So according to Hess's law, here we go. And I know this is a little messy, but I like Hess's law problems. I'm going to kind of stop here, and I'll do it 2 lines there. So when we add equations, I kind of think of a brick wall kind of as my reactants and my products. And if you have the same number of something on both sides of reactants and products, it cancels each other. Case in point, 1/2 mole of O2, 1/2 mole of O2. I've got 1 mole of CO, 1 mole of CO. That looks like it's about it. So everything that's left, I carry down. So I carry down 1 mole of carbon in its solid state, 1 mole of O2 in its gaseous state, goes to form 1 mole of CO2 also in its gaseous state. So the beauty of Hess's law, it's really not that complicated, says that if I can take these elementary steps and and they add together to make a reaction of interest, then the enthalpy associated with this reaction of interest is the sum of these two, which I don't have my calculator handy, but I can probably do that in my head. Yeah, I can do that in my head. So they're both negative, so you're looking at negative 393.5 kilojoules. Do you see that number over here? Mm-hmm. Okay, so I mean, it's not that complicated. Energy diagram, 2 elementary steps to get us to overall reaction. You know, that's Hess's law. So after I got to look, I'm like, oh, that's a pretty cool Stacks diagram. Now, Hess's law can only happen if it's a state function. Enthalpy, delta H, I guess it'd be, change in enthalpy state function. Yeah. What's that mean? It means it doesn't depend upon path. So, for instance, this last thing that we looked at, does this mean that this is and we're going to look at mechanisms in Chem 2, does this mean that this mechanism, these 2 steps are really the steps in the mechanism? Not necessarily, but mathematically, algebraically, they add together to give us our overall reaction of interest. We know those enthalpies, we add them together, we get the enthalpy of the overall reaction of interest. Does it happen with steps? I don't know. Maybe, maybe not. Okay. All right, so we're going to do, I'm only going to do 1 problem here, so it won't take very long. So we're going to do Hess's law problem, and it's basically the combustion of benzene. C6H6 is a benzene ring. It looks like this. So each of those little, we have carbons here, and as it turns out, we haven't talked about Lewis structures yet. But we have alternating single, double, single, double, single, double bonds. And then my 6 hydrogens are kind of connected there, where each one of those dashes are, there's a hydrogen. So that's benzene. And we're going to burn it, and 1 mole of benzene will burn with 15/2 moles of O2 to form 6 moles of CO2 and 3 moles of H2O. We talked about combustion problems before. So this is our reaction of interest. So when I'm working Hess's law problems, I got something blue that is totally leaking in my bag somewhere. And I try to chase it down. Oh my gosh. So this I call it the reaction of interest, RXN of interest. Okay? So in other words, delta H, RXN, don't know. Gonna find it. Here are our puzzle pieces. Now, in a Hess's Law problem for your test, for homework, I don't think they give you any puzzle pieces that don't fit. You have to turn them different ways. Sometimes you have to rotate them. Sometimes you have to make more of them to get what you need to get to the full picture. But these are our puzzle pieces. Now, before we work this problem, I need to talk about something in chemistry called allotropes. And allotropes, we're going to pick on carbon, because carbon, as you guys maybe know, is like if you have lead pencils, that's actually cute little carbon cute little carbon atoms that are arranged a certain way. That's carbon atoms. They call it lead, but it's not lead anymore, it's carbon. And then my diamond's carbon, your diamond's carbon, okay? It's got carbon in it, it's made of carbon. So that gives us a couple different allotropic forms of carbon. So all an allotrope is it's the same element, the same substance. Allotropes, yeah, are specific to elements, not other substances. An element that just is arranged differently. Of course, to get diamonds, you probably know that you have to do the whole dinosaur thing, the whole pressure and time to get diamonds. Graphite, not so much. So here we go. Carbon, meet carbon, okay? Carbon atoms. My point, the reason I'm kind of deviating here is I go back a few slides. The allotropic form of carbon that's standard is in its graphite state. Well, no kidding, right? So that just means when we work a Hess's Law problem, to be really correct about it, which we want to be really correct about, we have to say if there are multiple allotropic forms, which form is it? That's it. So let's look a little bit more at carbon, the different forms, allotropic forms of carbon. So this is what a diamond would look like. So the properties of how those carbon atoms are bonded together and arranged give the properties of a diamond what it has. This is the graphite in our pencils, kind of more like a sheet thing. But actually there are two more allotropes of carbon that are maybe not as commonly known, maybe they are, as graphite and diamond. Another one is buckyballs, and there's actually some history that intersects with astronomy, that buckyballs, I think this is right, were actually first found on meteoric material. Like, if you know what a meteor is, it's basically a space rock that made it through Earth's atmosphere, and it's something that you can pick up and examine. So you figure, well, that kind of makes sense. In outer space, what do you think? Are there different temperature conditions, different pressure conditions that allow for carbon to come and do that? The buckyball thing. There's a buckyball. And then this is like the fourth one. Graphene, not graphite. Graphene is really strong in the sheets, and there has been some talk about making like almost a type of elevator to go beyond into outer space, basically. So of course, I know we have the troposphere, the stratosphere, the mesosphere, and the thermosphere, then we outer space. Okay, so basically take something strong and make a rope so you can. That reminds me of Jack and the Beanstalk right now, but I don't know. I don't think there's any golden goose up there. So this is another way to arrange carbon atoms, and it's very strong. Definitely has industrial uses. All right, so back to the point at hand. I did all that just so we kind of know a little more about chemistry and how elements can be different allotropic forms, and then also to say why it's important to specify that it's in its graphite state. Although with that said, if you're working problems, because on my answer keys I don't take the time, if you're working problems and you're using carbon in its solid state, I usually put carbon solid, but I don't usually put graphite. But anyway, these are our puzzle pieces, and these are the enthalpies associated with those puzzle piece reactions. Now, before we kind of finish up with Hess's Law, how this works. Remember what we learned earlier. We said two important tools that we can do with any reaction. We can scale it up. Remember, if we scale it up, then you have to scale up your delta H. So just remember that, because we're going to have to use that, so it's in the toolbox. The other thing is if it's not in the right direction, if we need to flip it, remember then all we got to do is change the sign of the delta H. And I'll warn you that sometimes you need to do both. Sometimes you need to flip it in order for it to get down the road. What do I mean by down the road? I mean, you're trying to, this is your target, okay? And you need to manipulate what you're given in order to get to your target. And I'll kind of show you clues to how to work those. And so I apologize in advance a little bit because I'm going to kind of take you in a basic Hess's law, and in your homework, you're probably going to have to kind of think outside the box a little bit, or I'll kind of tell you what other twists and turns a Hess's law problem might have.
So the first reaction is what we need.
Yes,
Okay.
Yeah, this reaction is like this reaction.
Okay.
Yep, and these are our puzzle pieces, yeah. Yep, and these are these. But the problem with these 1, 2, and 3 is they might not be in the right scale, and they might not be directed in the right direction. Yeah. So, the way I would do it is I compare my puzzle pieces. So these are the puzzle pieces with the overall reaction of interest. And I try to focus on something that's unique. So, for instance, if we look at this guy, the first one, do you see where I have 1 mole of C6H6 on the product side, but what I want or what I need is on the reactant side? So here in a minute, you're going to see puzzle piece 1 flipped around. I flip it around, I got to change the sign of the delta H. If we look at the second one, you have to be careful because, for instance, O2, you know, I can't focus on the O2 because it's in my third piece also. But what's unique to my second piece, to me, looks like the CO2. And every once in a while, I make a mistake, and you get down the road, you're like, oh, drat. And you look back, and you're like, now I know what was wrong. But CO2 is unique. So notice that I have 1 CO2 here, but where I'm trying to get down the road, my overall picture has 6. So what can I do? Scale it up. So I can scale this whole thing up, and then I'll have to take this times 6. Let's see, the last one, and isn't this, I just think this is so exciting, because you're like, H2, well, there's no H2. Well, our H2 better cancel out. And actually, while I'm at it, I'll tell you that that's a hint sometimes. Actually, you have to use that to your advantage. The H2 introduced somewhere else needs to be canceled out by the H2 introduced somewhere else if there's no H2 in your overall reaction of interest. So I'm warning, that's one of the things. But H2O is unique, isn't it? So, times 3. This one's not too bad. So let's see what that looks like. So, and I use these, it's called prime with that little tick. Okay, so that's puzzle piece 1, and we're gonna focus on the C6H6. And so this little tick mark right here, that's my prime. So 1 prime, it's got the little tick mark there. So the difference between what I was given 1 and 1 prime is I went ahead and reversed it. Okay. So then now my delta H not 1 prime looks like this. Which, since we reversed it, what we got to do is change the sign. So this is the sort of problem where you have to pay attention to detail as you're working it. And I already said sometimes you'll get down to what feels like a dead end. And then, like, I don't know if we run into this when we're trying to put a puzzle together, but we have to kind of backtrack. So here in a minute, that 1 prime is going to be one of my things up here. All right, so let's look at 2. We said 2, we're going to focus on the carbon dioxide. So you guys said I could scale it up. So 2 prime would be this, where I scale it up. Instead of 1 mole of carbon, I have 6 moles of carbon. Instead of 1 mole of O2, I have 6 moles of O2. Instead of 1 mole of CO2, I have 6 moles of CO2. And this is simply times 6. So if you take negative 393.5 kilojoules of energy, which seems like a lot, you get negative 2,361.0 kilojoules. And can you see where that's my 2 prime? In working any math problem or physical science problem, this is nothing new to general chemistry. The more organized you can be, the better off you'll be. It helps you, the writer, and it helps the reader know what you did. So that's going to be this one right here. It's the 2'. And then 3, we said we could focus on the H2O, multiplying through by a factor of 3. So 3' would be 3H2O. Now this is where you have to kind of make sure you get your fractions okay. So 1/2 times 3 is equal to 3/2. 3/2 moles of O2, and then of course 3 moles of H2O. Our delta H3' will be that negative 241.8 kilojoules times 3. So that's negative 725.4 kilojoules. Now, I guess I'm trying to think of an analog to putting a puzzle together. We can't assume that this is going to make the right picture. We have to verify that. So here in a minute, one of my next steps is going to be to line up 1', 2', 3', add them together kind of like I did over here, and make sure that this overall reaction of interest is the combustion of benzene, which is what I was after. All right, so here we go. And if it is, then all I got to do is add up their delta H's. Delta H1' plus delta H2' plus delta H3'. So yeah, you call that little tick mark a prime. It just means you manipulated the original one. So here's our 1', 2', 3', shown on the previous page. So I would probably line up my reaction arrows like if I was doing this on a regular piece of paper. But just so you know, we're on the same page. We have reactants and we have products. First off, I'm going to try to clean things up. Notice I can make my carbons cancel, okay, because I have 6 moles of carbon on the product side for 1', 2 moles of carbon on the reactant side for 2'. Anything else I can clean up?
The 3.
Yep, the 3 H2s. Very good. I think that's the only thing that cancels. Now here's one for you. I can combine my 6 and 3/2. Now sometimes students will ask me, well, Mrs. Snipes, and I don't know if I don't want to confuse you, but what if I had like a plus, what if on the product side somewhere I had plus 3 moles of O2 that were also formed? Well, then I would have to be subtracting those, and so I would have to add these and this one, but that's not the case. So combining, and if you're like me, I don't do a lot with fractions, but fraction-wise, if we were to put 6 into halves, you're looking at 12, right? 12/2, 6 is 12/2. So if you take 12/2 plus 3/2, you get 15/2. And so actually that's exactly what you're going to see down here, 15/2. Which seems weird, but chemistry is kind of odd sometimes like that. 15/2 is correct. So here we go. All we got to bring now, since we combined the 15/2 together, we just bring down what didn't cancel. So C6H6 did not cancel. We have 15/2 O2, 6 moles of CO2, and 3 moles of H2O. And here's where you just get warm fuzzies inside. And you're like, oh, that was what I was after. Okay? It's not magic. But this is an important step. So what you have convinced yourself is those 3 smaller reactions do in fact add together to give us the overall reaction of interest. So then that means their enthalpies of reaction can be added together. Okay? So it's an important step. So it looks like this. So we bring along what we knew about our enthalpies, delta H1', delta H2', delta H3'. And then we add them together. All exothermic? Should be very much exothermic, huh? So I'll just tell you. And remember, since we're adding here, we don't do as much adding in chemistry as we do multiplying and dividing. We round according to decimals, so you're looking at 1 decimal. So the answer would be a whopping 3,000, I feel like I'm on The Price is Right, 3,135.4 kilojoules. Negative exothermic. So we probably could have knocked out heats of formation. But your test isn't until a week from Thursday, right? So I think this is the right thing to do. So that's as far as I wanted to get today. Dun dun dun. Go enjoy those problems. They are kind of fun.